My pleasure to introduce Markus Aspelmeyer, who is Professor of Physics at the University of Vienna, and he's Speaker of the Vienna Center for Quantum Science and Technology. Markus is one of the pioneers of the field of cavity optomechanics. His research combines the development of new quantum technologies with fundamental quantum experiments. So please join me in welcoming to give a talk on cavity quantum optomechanics, Markus Aspelmeyer.
Thanks a lot. Thank you so much. Thank you very much, David, and the other organizers for having me here. I have to apologize for my voice. I attended the Super Bowl this weekend, and my voice got lost somewhere in the last 5 minutes of the game or so. But what I'm going to do is I would like to introduce you to the idea of controlling massive mechanical objects in a quantum regime by exploiting the toolbox of quantum optics. This actually has some very exciting consequences, both for foundational questions in physics and for applications in the classical and also in the quantum information processing domain. And the talk is essentially an attempt to share my excitement about this topic with you. So, if you think about mechanical systems in physics, then you will find that they have predominantly a history in sensing. So a particularly impressive example from my point of view is one of the very first successful measurements of the density of the Earth, nowadays also known as a measurement of the gravitational constant. So there's an experiment that took place 20 years before the seminal experiment by Cavendish, and the idea was to measure the gravitational attraction between a mountain and a pendulum. And the deflection of the pendulum was essentially measured via calibrating it to the fixed star background. The value was quite accurate, and the main source of error in that measurement was essentially by the not known mass distribution of the mountain. And we all know that Cavendish's experiment was then much more accurate. During the next 240 years or so, mechanical sensing has really significantly advanced. And today we have amazing levels of sensitivity for mechanical devices. I just put up here a couple of examples. We have, for example, just using mechanical oscillators, nano-micromechanical oscillators, we have sensitivities on single electron spins and even single nuclear spins. We have displacement sensitivities on the attometer scale. We have force sensitivities on the zeptonewton scale, mass sensitivities on the octogram scale. So nowadays people can detect individual atoms being deposited on a simple mechanical system. Now, the main limitation at this stage for all these sensitivities is actually the fact that those systems are classical harmonic oscillators. So there's Brownian motion that limits, in most cases, the sensitivity of these devices. And it's therefore an extremely intriguing question to ask, where would all those numbers here go when you actually push into the regime of mechanical systems in the quantum domain? Maybe even create non-classical states of mechanical systems squeezed in their position to really go significantly beyond these levels of sensitivities. And this is one of the big motivations why people have started to look into the quantum regime of mechanical oscillators. Actually, there are a couple of other motivations that contributed equally to these developments, namely quantum foundations and possibilities for new architectures in a solid state domain for classical and quantum information processing. Let me just give you the main idea behind that. So in the case of quantum physics, one of the very fundamental puzzles in quantum physics is the so-called measurement problem, also known as the Schrödinger-Cat paradox. So according to quantum theory, if you have a single photon somewhere and it impinges on a 50-50 beam splitter, then the location of the photon behind the beam splitter is intrinsically undefined. It's actually said it's in a superposition of both possible locations. If you combine this superposition now with an evil device, then what you end up with is possibly a superposition state that contains the state of a cat that is alive and at the same time of a cat that is not so much alive. Right? And this is the well-known Schrödinger's cat paradox. And the possibility of such superposition states poses a fundamental challenge to our current worldview. And some people even suggest that this is the reason why quantum physics should actually break down when you go to more and more macroscopic systems. And Einstein summarized that very nicely, this paradox that we encounter here in a letter that he wrote to Schrödinger in August 1935 by saying, you see, once you have such a wave function of your state, there's by no art of interpretation can this psi function be made an adequate description of physical reality. Now, mechanical quantum systems enter here the stage as really a new and very promising player. So what you can think of now is whether it's possible to create mechanical cat states. So is it possible to create superposition states of different center of mass states of very massive objects? For example, such a cantilever being a superposition with the center of mass being in this location or the other location. The third aspect that I was mentioning was information processing, quantum information processing. And why mechanical systems play an interesting role here is because you can functionalize them. Once you have such microfabricated devices, you put a mirror on top, you couple to light. You put something conducting on top, you couple to charge. You put a magnet on top, you couple to spin, and so on and so on. So your mechanical system can actually couple to many different other physical systems, and thereby can act as a transducer between different physical systems. So once you achieve coherent coupling between your mechanics and one of those physical systems and your mechanics and another physical system, you can start suddenly interconnecting photons with magnetic flux qubits or something like that. So you can interconnect different quantum systems that normally wouldn't interact with each other if there wouldn't be any by direct interaction. There have been a couple of proposals out there. I just mentioned one here by essentially Peter Rabel and Peter Zoller, Michel Lukin, where they proposed that by using an array of mechanical oscillators, you could actually have long-range interactions between individual spin qubits that are implanted in a solid-state matrix. So the idea would be you have here a magnet on top, then you get a position-dependent Siemens splitting of your spin here, therefore you couple to the mechanical motion, and the mechanics you can couple, for example, electrostatically in an array, and suddenly you have long-range interacting qubits, which could be a very promising architecture for solid-state-based quantum information processing. And there are other proposals out there how you could do long-distance quantum communication and so on. Now, the interesting point about that is that such mechanical quantum transducers already exist. And they already exist since a very long time. So where do they exist? Well, they exist in trapped ion-based quantum computing. In fact, the realization of quantum gates in such trapped ion quantum computers relies on the quantum aspect of the joint mechanical motion of the string of ions. So the way you interact individual qubits in the string of ions is to actually couple to the normal mode motion of this mechanical motion in the quantum regime. And this is at the very heart of the seminal quantum gate by Ignacio Serac and Peter Zoller. So in essence, what I'm going to do now is I will just make blatant use of all these concepts that have already been developed in the context of this trapped ion and atomic physics quantum information processing, and will apply that now not to 5, 7, or 10 atoms, but to the collective motion of 10 to the 10, to the 10 to the 15, 10 to the 20 atoms. And that is the main idea. So I will try to show you now how we can combine radiation pressure on large mechanical devices together with the toolbox of quantum optics to enter a regime of quantum-controlled mechanical systems. Radiation pressure, and this is the only the only historical excursion that I'm going to take you on, is a well-known phenomenon in physics. It has essentially been proposed for the first time, conjectured by Kepler, in order to explain why the tail of a comet is inclined with respect to its motion around the sun. In 1901, there was a back-to-back publication by Lebedev in Moscow State and by Nichols and Hall in Dartmouth, who for the first time unambiguously demonstrated the effect of radiation pressure. And of course, radiation pressure is at the heart of many important developments in modern optics. In particular, it's at the heart of trapping, cooling, and manipulation of atoms, which is the basis for modern AMO physics. And it's also at the heart of optical tweezing, which has become now one of the very important tools in biological physics. So if you look at the effect that a single photon has on a mechanical system, so just you take a reflectively coated AFM cantilever. You send a single photon on this thing, and then you see what the effect is just upon reflection of the photon. And what you will find out is there's no effect. The mechanical system remains essentially unchanged. However, what you can do is you can take a second mirror and make a cavity such that the photon bounces many times. And then you get something interesting. First of all, you get in trouble. And this is something that has been realized already in the 1980s in the context of gravitational wave detectors. So at that time, so you know gravitational wave detectors are large-scale optical interferometers, several kilometers long, that are built in order to detect essentially the variations in the strain of space when a gravitational wave runs through Earth. That's the main idea. So it has to be very sensitive. Now, in order to make an interferometer very sensitive, you have to crank up the optical power to increase the sensitivity. And then an interesting question came up. In the 60s, it was realized, in particular by Glauber, that due to quantum physics, there's an intrinsic amplitude noise in a laser, so-called shot noise. So Carl Caves posed the following question. You see, the interferometers are now being developed to detect gravitational waves, work by measuring small changes in the position of free masses. As I just explained it to you. There has been a controversy whether quantum mechanical radiation pressure fluctuations disturb this measurement. This letter resolves the controversy. They do. So what's the point behind that? Well, if you look at the phase noise in such an optical interferometer, when you have a fixed integration time, then you see when you crank up the optical power, your phase noise, so your phase sensitivity increases with the root n of your number of photons. This is just improvement over the shot noise in your laser beam. However, due to radiation pressure back action, you start to hit the mechanical system, so your interferometers mirrors, and you start to introduce additional noise, which is called the back action noise. So what you see is that you end up in a trade-off between unavoidable back action noise due to shot noise and the shot noise limit. And you get a minimal phase noise that you can achieve in such an interferometer, which is known as the standard quantum limit. And it turns out only now there have been two very beautiful experiments, one by the Stemper-Kern group in Berkeley and one by the Riegel group at Schiller, who demonstrated for the first time exactly this regime, that a mechanical system is really driven by the shot noise of mechanical of the laser field. Now let me introduce to you in a very few slides the basic assets that you can get. This is a nuisance, and that's why for a very long time the combination of quantum optics with optomechanics has been considered to be a bad thing, because you simply introduce noise. But if you think about it a little bit more, you realize that you can do, well, actually very interesting stuff. So here's the idea. And these ideas go back also to the gravitational wave community. Predominantly, Vladimir Braginsky was the one who thought first about it and did the first seminal experiments on that. So here we have our cavity. Here's the our mechanical mirror that can reflect light. We have a second mirror such that photons are now confined inside this optical cavity. And if the wavelength of the light that pumps the cavity, if the length of your cavity is a multiple of the wavelength of the light that pumps the cavity, you get a resonant enhancement inside the cavity. Right? So this is then your cavity resonance. Now, there are two fundamental effects that are of importance here. First of all, depending on the intensity, the radiation pressure will just push your mechanical system further. So you get an intensity-dependent displacement. This leads to a cavity bistability, which has been observed for the first time in the 1980s by the group of Herbert Walter in Munich. But there's more to that. Because depending on where the light is reflected inside the cavity, the light that gets out of the cavity will have a different optical phase. So if you put these two together, you get an intensity-dependent phase shift of the light that is reflected from such an optomechanical cavity. An intensity-dependent phase shift, we know in optics what that is. That's a nonlinear optical medium. So we have just created, just by taking a cavity with a moving mechanical boundary, we have just created a Kerr-type medium, which is able to generate, for example, squeezing in the input light. And in fact, that is something that has recently, this is an advanced online publication, just recently been demonstrated by the Stamper-Kern group in Berkeley, where as a mechanical oscillator, they take a cloud of ultra-cold atoms and they look at the center of mass motion of the cloud, and that moves inside an optical cavity, and you can exactly do the trick, and they demonstrated for the first time optical squeezing with this atom-mechanical, optomechanical system. Now, this is the one interesting effect. All we looked at was that we are driving the cavity here on resonance. Now, what happens if we slightly detune the cavity? So assume that we actually look now at a situation where our intracavity intensity is somewhere here. So the length is slightly detuned from resonance. What happens now when the mechanical system moves? Well, you see the mechanical system moves and changes the intracavity intensity, which means that the intracavity radiation pressure force on our mechanical system changes. So we have just introduced, just by detuning the cavity, a position-dependent force onto our mechanical system. And that's physics 101. I have an harmonic oscillator. I introduce, in addition, a position-dependent force. I change the spring constant. And that's what's called an optical spring. And that has been first demonstrated by the Karai group in Munich back in 2003. Now, there's one more to that. I only told you half of the story. If I change the cavity length, it will take a finite time for the intracavity field to adapt again. It will actually take the cavity decay time for the field to change its intracavity intensity, which means that the force, the position-dependent radiation pressure force is retarded in time due to the finite cavity decay. What does that mean? Again, physics 101, I have a mechanical oscillator, I have a position-dependent force, I retard it in time, position becomes momentum if you retard it in time for an harmonic oscillator, so I just introduced now, because of the finite cavity lifetime, a momentum-dependent force. And that allows you to change the damping. Okay? So now suddenly you can just, in a detuned cavity, you have full control over the mechanical susceptibility. You can either increase the damping, and this leads to cooling, as we will see, or you can reduce the damping and start to parametrically drive the system, put some energy into the mechanical system taken from the optical field. So in a way, you have an optomechanical heat engine, if you want, right? Where exchange takes place, heat exchange takes place between the optical field and the mechanical system. Now, of course, you can also have a quantum picture, and this has for the first time been demonstrated in the group of Karivahala at Caltech. You can also have a quantum picture, so I apologize, this is the very brief version for the quantum optics people here in the audience. The quantum picture, if you have the strongly driven optomechanical cavity, for the case that your cavity line width is much smaller then your mechanical resonance frequency, which is the so-called resolved sideband regime, you can think of it in the following way. So here's your optical cavity, here in frequency space is your cavity resonance. If you drive now off resonance, so your cavity is detuned, you see that the only way to actually scatter photons into the cavity is by getting some extra energy. Because this is at lower energies, right? Where does the extra energy come from? Well, if you're detuned by the mechanical resonance frequency, the extra energy can come from the mechanical system, right? So what you do is you scatter a photon inside the cavity by annihilating a phonon of your mechanical system. And of course, if you pump long enough, the inverse process is also true. And what you get now is a coherent energy exchange between the optical field and the mechanical system. And in two-mode quantum optics, this interaction is known as the beam splitter interaction. So this allows to coherently transfer quantum states between one system and another system. It's used in atomic physics, for example, to store light into atomic vapors and so on. Now, and you also see if your cavity decay is very large compared to the coupling rate, at the moment you scatter a photon in there, the photon carries the energy of the phonon and it leaves immediately the cavity afterwards, it takes the energy with it. And so you effectively cool your mechanical system. Now this is simply laser cooling of your mechanical system via this moving cavity. What you can also do now is you can pump on the blue side, and you see the same thing applies here, same argument. The only way to scatter photons into the cavity is by getting rid of some energy, and what you do is you jointly excite an optical and a mechanical excitation, and this in two-mode quantum optics is known as a two-mode squeezing interaction or a parametric down conversion interaction. That is the way to generate quantum entanglement between the light field and the mechanics. So now, from a quantum optics point of view, once we realized that, we were extremely happy because we have everything together. So what we have now is we have a full quantum optics toolbox to prepare and control mechanical quantum states just by using optical quantum states. That's it. That's all you need to have. Right? Of course, there are a couple of challenges. Challenge number one is, in order to make use of those very nice quantum mechanical interactions, you have to be able to apply them on some pure initial or relatively pure initial mechanical states to begin with. So therefore you have to extract entropy out of your mechanical systems and essentially you have to cool them. So this is why people are so much interested in cooling the center of mass motion of such mechanical devices in order to prepare low entropy states and start being able to do quantum control on them. The other thing is, you see we have a cavity here. So we have essentially decoherence. The photons leak out of the cavity, the phonons leak out of the support. So what you have to make sure is, in order to exploit this coherent quantum interaction, is that your coupling rates overcome all the decoherence rates in your systems. And that is typically fulfilled in a strong coupling regime, sometimes also in a strong cooperativity regime. And now I just give you one figure as a take-home message. In two-mode quantum optics, so this I should mention that. So both of these requirements have been achieved individually in different experiments. And now the big challenge is to put them all together and combine those two things in one single experiment and really demonstrate full quantum control. Now, here's the take-home message for two-mode quantum optics. For quantum optomechanics. In two-mode quantum optics, I stole this picture from a paper of Jeff Kimball. You normally have a nonlinear crystal. You have two optical modes seeded by a pump in this nonlinear crystal, and this nonlinear interaction here essentially correlates the quadratures of the two optical modes, and then you can do nice quantum physics with it. Now, here's what you need to take home for quantum optomechanics. In quantum optomechanics, the nonlinearity is provided by this cavity. I told you that already. And the only thing we do is we replace one optical mode with a mechanical mode. That's it. That's the only thing you have to remember. Now you know everything about quantum optomechanics. And now the rest is now just storytelling. Now the fascinating part is you're not restricted now to just one mechanical system. The different systems that people have been realizing now since the last couple of years, they span a huge range of frequencies. You see here from hertz range up to some tens of gigahertz, and mass scales from a few thousand atoms up to kilogram scale objects here with mirrors of gravitational wave interferometers. Other examples are, for example, here waveguides evanescently coupled to some substrate. Here's photonic crystal cavities. I will say something about that soon. This is actually an LC circuit. So what we have here is a microwave cavity where this membrane here is one part of a capacitor. So you modulate the capacitance in an LC circuit, which is nothing else than a microwave cavity coupled to a mechanical system. Here you have toroids where you have where you can couple light in here, and you have internal total reflection in this toroidal structure, such that the radiation pressure to the outside of the structure leads to mechanical breathing modes of the system. You have freestanding coatings, you have micromechanical membranes that you can put in the cavities, and so on and so on. So this is the interesting aspect here that is that you have this one universal coupling mechanism that applies universally to all of those different systems. Now, I will rush you through a couple of recent results in the field to show you the variety of the different approaches. So I told you strong coupling and cooling to the ground state are the two essential ingredients. And both of those have actually been realized. So here's one example of an experiment that we did some time ago where we demonstrate, so where we have here our mechanical oscillator, silicon nitride with a mirror pad on top. You use that as the end mirror of a Fabry-Perot cavity. You can put that in a cryostat. And then what you have is you basically have two optical beams that interact in the cavity. One is just a very weak beam that is resonant with the cavity to read out the mechanical motion. The other one is a detuned beam that does the physics, that drive the system, and then you can actually have two independent homodyne detection setups that independently detect the optical cavity field quadratures and the mechanical motional quadratures. And then you can start correlating them, and in the regime of strong coupling, that regime essentially means that your mechanical states get now addressed via the optical field. So what you obtain is a genuine hybrid optomechanical system. The energy spectrum cannot any longer be explained just by one individual system, but it's now a strongly coupled system, and you get a splitting essentially here of the energy output spectrum of the cavity. So, and this has been also done recently at much lower temperatures in other experiments. Now, so the strong coupling is not a problem. What about cooling? So cooling is something that people started in the very beginning. So essentially, after first experiments by Khalid Karai in 2004, who still used photothermal forces, 2006 started avalanche of experiments. So you see here 2 years, there's a set of back-to-back publications that all demonstrated radiation pressure-based laser cooling. And once again, the idea is simply if you pump your cavity off resonant, you get scattering, Stokes and anti-Stokes scattering of photons, and what you do is with a detuned cavity you resonantly enhance one of the two scattering processes and you extract energy out of your mechanical system. And it has also been realized quite early on that there's a one-to-one analogy to the Seipen-resolved cooling of ions, as I explained to you in the very beginning. So this is all the principles really are the ones that underlie also these trapped ion quantum physics. And over the years, more and more groups actually started to enter the quantum regime, and in 2011, a number of groups around the world have managed to cool their systems close to or even into the quantum regime. I just show you one experiment that has been performed in a group of Oscar Painter at Caltech here, and this is a so-called optomechanical crystal structure. So what you have is the system is an integrated optical and nanoscale resonator that is formed here in the surface layer of an SOI wafer. So you have a periodic patterning here that essentially forms a Bragg condition both for the electromagnetic waves and the acoustic waves. You introduce a tiny defect here in the middle and you co-localize the photons and the phonons in the center of the structure here. And thereby, by deforming now the structure via mechanical motion, you very strongly affect your cavity resonance frequency, which means you have very strong optomechanical coupling. The frequencies here are in the gigahertz regime of the system. So if you pre-cool this chip here, this is somewhere in the regime of 20 Kelvin, you have 100 phonons left in the mechanical motion. You launch now via a fiber taper light into this cavity. You start to detune it to the red side, and you start to extract gradually energy out of the system, and you cool the mechanical motion down to the quantum regime. And by now there are several systems that have been demonstrated in the quantum regime. I just show you a couple of them. This is a particularly nice example that doesn't have to do anything with optics. In that case, this is a 6 gigahertz acoustic resonator. So you have thickness oscillations in an aluminum nitride membrane. This is directly cooled to the quantum ground state by putting it in a dilution refrigerator and then coupled to a superconducting qubit, and then basically achieving single phonon control of such a resonator. So there's one thing I did not yet mention to you. The intrinsic optomechanical coupling is genuinely nonlinear, highly nonlinear. So what I only showed you so far is a strongly driven optomechanical cavity. And this is a situation that's very reminiscent of atom optics. So if you have a two-level system, so just a two-level atom that is driven by a strong light field, what you have is you saturate all the lower levels, and all the upper levels then get dressed by your, by your optical radiation fields, and your level spacing here becomes equidistant, and you have a sort of linear system that also shows this normal mode splitting in the form of a Mollow triplet. It turns out this very same thing is true for the optomechanical case. So if you now look at a very weakly driven optomechanical system, so one where your optomechanical coupling rate on the single photon level is strong, you start to see strong nonlinearities. You get strong photon-phonon coupling that shows the very similar physics to a two-level system, and you can enter a completely new regime of quantum physics with those mechanical structures. And that is why one of the big challenges right now is to see whether one can achieve the single photon strong coupling regime and then enter this regime of very strong single photon nonlinearities, strong photon-phonon couplings. And one of the interesting aspects, for example, from an application point of view, is what you could envision is that you could build a single photon optomechanical detector. So where the arrival of a single photon would actually shift your cavity frequency to such an extent that you can detect it, and it would even be energy resolving because the shift will depend on the momentum of your photon. So there are very interesting possible consequences once you manage to reach this regime. Another question, and then I will show you a couple of examples, is there any way to avoid working with cryostats? Right? And in the lab, this is really something, this is really a non-trivial task, and it turns out if you do the numbers, I will just summarize the result here. What you have to do is you have to operate in a regime where your decoherence rates of your system, even at room temperature, are sufficiently small compared to the coupling rates that you can achieve. And it boils down that you get conditions, for example, for the QF product of your mechanical system, because your mechanical dissipation rate needs to be very small. And you get some conditions on the cooperativity rates that you can achieve. And there have been some novel approaches that people have been suggesting, maybe operating in a pulsed regime where you basically operate on timescales that are short compared to the thermal decoherence rates in your system. Now, let me use my last minutes to run you through a couple of examples what groups around the world have recently been doing with such optomechanical systems, what they have used it for in different applications. So here's one example by the Tang group in Yale, who demonstrated by using a cavity optomechanical system a mechanical non-volatile memory. The idea is very simple. You have a mechanical beam that operates near mechanical bistability, so you can define an upstate or a downstate, and you make this mechanical beam now part of an optomechanical cavity, such that your cavity resonance frequency is different for those two different states. And what you end up with now is the possibility by optomechanical driving, you can actually excite such a state. So when you are in one specific state, you excite it by parametric driving the system, and then you can selectively cool it down to one of the two states, again, just by optomechanical cooling. And you can also read it out just because you can differentiate the two mechanical states. So what you have now is really a non-volatile nanomechanical memory cell that is exclusively operated by light. And reading and writing is really optical and optomechanically. Another nice on-chip application might be due to an effect that has recently been discovered by the groups of Oskar Painter and Tobias Kippenberg, which they called optomechanically induced transparency. It's an analog of electromagnetically induced transparency, where essentially an interference effect between scattered photons, so sideband scattered photons from the mechanics, lead to a transparency window in your optical cavity. And once you have that, you can play the tricks that people do in electromagnetically induced transparency. You can essentially modify the dispersion relation of your medium. If you now have an array of such cells with such optomechanically induced transparencies, you can start to slow and stop light and then basically build a mechanical optical memory cell. This same idea has been used recently by the group of Eugene Polzig at the Niels Bohr Institute in Copenhagen to come up with a proposal how to have a noiseless optical readout of an LC circuit at room temperature. And the main idea is now if you have your LC circuit, you have your resonance here, but if you couple it to a mechanical mode, then you can achieve at the mechanical frequency this transparency window, and if you operate exactly at that point, you have a very low noise, so high signal to noise ratio optical readout of your LC circuit. And that is also at the heart of different proposals for hybrid optomechanical systems, where now you couple an optical system to a microwave system, for example, which then can, for example, also lead to really interconversion of microwave photons to optical photons and so on. So this is really, I think, a very powerful tool. Here, another example application is a recently fabricated new type of accelerometer by the Painter group at Caltech. So here you see this huge mass that is now that is optically coupled to this small optomechanical cavity. So you have just an evanescent optical wave coupling these two bridges, and you get a very high sensitive readout and high acceleration sensitivity with this device. Furthermore, the interesting part here is that you can tune the dynamics of the sensor via optomechanical interaction. So this is really a new type of performance for such integrated sensors. The last practical application I would like to mention is something that came completely out of the blue, and on first sight doesn't have to do anything with this research in optomechanics. And it's related to the so-called thermal noise problem of optical coatings. So it turns out that for applications like gravitational wave detectors and for ultra-stable lasers, the Brownian motion of the coating itself of your cavity mirrors places right now the fundamental limit for the sensitivity. And you see the Brownian motion, so the Brownian fluctuation of the coating is linked via the fluctuation dissipation theorem to the mechanical dissipation in this coating. So if you can come up now with a coating that has less dissipation than the coatings that are less mechanical dissipation than the coatings that are now being used at the moment, you should be able to produce mirrors that overcome this thermal noise limitation of current high performance interferometers. And that was exactly one type of research that we have been pursuing in Vienna, that we investigated optomechanical effects in freestanding optical coatings, and basically by incident developed now coatings that have, because of the requirements for our quantum experiments, high reflectivity and at the same time high mechanical Q. So the idea was now, instead of making a resonator, why not just making a mirror out of that, use that mirror in a high finesse optical cavity and see whether you can reduce now the thermal noise of your cavity in such an experiment. Turns out this is possible. It was in a recent experiment we could show that you do actually get a tenfold reduction in this coating thermal noise by using semiconductor single crystalline coatings compared to the regular ion beam sputtered silica tantalum pentoxide coating. So this has been in collaboration with the group of Junyi in Chile, and with, to my knowledge, one of the first spin-off companies from this whole quantum optomechanics fields, crystalline mirror solutions. So this was my show over the applications, possible applications, and I have to stress, I think this is just the beginning, right? I mean, this whole field just started 5-6 years ago, and we are only now entering the stage where practical applications start to come out of this whole thing. Now let me go back to the very first motivations. I told you one of the motivations, that was my motivation to enter this field, is really fundamental questions in quantum physics. So let me essentially rephrase the question that I asked in the very beginning: who actually killed Schrödinger's cat? So this is the big question. When you try to create a macroscopic quantum superposition, either coupling to the environment by standard quantum physics will destroy your coherence, or some people even suggest there's new physics around that will collapse your wave function. So can we, by exploiting now mechanical systems in a quantum regime, generate such a superposition? And one possible idea is to generate a superposition state of, let's say, a particle being in this, being here and there at the same time, right? So that's one possibility. How could you do that? Well, what you could do is you could take a free particle, you could cool the center of mass motion of the particle to its quantum ground state. Then you can just let it drop. Then you have dispersion of the wave packet of your massive particle. And then you introduce something like a double slit or so, just some block or some other means of conditionally preparing by not detecting something here, a superposition of the sphere being either on the left side or on the right side. That's one possibility. How feasible is that? Well, turns out, how can you create such a state at all? And the idea is, again, use quantum optomechanics. Use a free particle, trap it inside an optical tweezer, put a cavity around that, and basically now do laser cooling of the center of mass motion. And that is something that we are doing currently. So we do have an optical cavity with here a single particle between the cavity mirrors that is trapped. It's a 250 nanometer particle. We see already first instances of laser cooling of this particle, and now the challenge is to cool it down to the quantum ground state. So my very last comment is on the long-term future. So here's the ultimate experiment that I would love to see. It's an experiment that Feynman put forward in the 50s at a gravitational physics conference, where he said, look, if you were able to produce from a macroscopic object a superposition of the object being here and there, and then just via gravitational interaction generate an entangled state between those two balls, then you are facing a fundamental challenge. He says, if you believe in quantum mechanics up to any level, then in order to describe such a state, you really have to believe in gravitational quantization in order to describe this experiment. So that, for me, would be the ultimate experiment to go to. And of course, well, you need long preparation, fall times, and so on. So maybe space is then the ultimate environment to do something like that. Okay, so let me wrap up. I hope that I could convince you or that I could convey a little bit the spirit of this new playground where we try to add quantum to mechanics. And I guided you a little bit through the possible implications for the foundations of quantum physics, for quantum and classical information processing, and for measurement theory, and for high sensitivity measurements. Of course, optics is not the only field. There are many other experiments around in the world where people couple different systems to charge, to spins, and I simply don't have the time to tell you all about that. But I would love to acknowledge my group here. I would like to introduce you briefly to the people who are responsible for the work. Gerrit Cole here on the coating side, Nikolai Kiesel, Diana Kaltenbeck on the levitation side, Witlef Wijorik, Simon Gröblacher on the quantum information side, and Sung-Kun Hong and Michael Wenner on the quantum gravity and pulse state preparation side. With this, I would like very much to thank you for your attention. I would like to thank my colleagues all around the world for providing me with input for this presentation. And I end here with a typical discussion that's how quantum physics is being done in Austria. Thank you very much.